Supernovas are a big, giant, dramatic end to a star's life.
For years, astronomers have watched one of the brightest and most mysterious stars in the night sky, knowing its end was coming, but never knowing when. Betelgeuse, the red supergiant in Orion's shoulder, has always felt like a warning light in the heavens. Unstable, swollen, and visibly changing even within a human lifetime. Scientists predicted collapse. They expected violence. They just didn't know if anyone alive would witness the moment it began. Now, according to this narrative, the James Webb Space Telescope has captured what many thought we might never see: the beginning of Betelgeuse's explosion, a stellar death, a cosmic shockwave, a direct window into the raw mechanics of a star tearing itself apart. This is not framed as just another deep space observation. It is presented as a once-in-a-lifetime event, the closest supernova humanity has ever recorded. And what Webb reportedly saw has changed everything. Betelgeuse is no ordinary star. Located in the Orion constellation, it is a red supergiant more than 700 times wider than our Sun and roughly 20 times as massive. For decades, astronomers have known it was unstable. It has swelled, dimmed, brightened, and erupted, behaving less like a fixed point of light and more like a living engine under strain. Then came the famous dimming in 2019. Suddenly, Betelgeuse faded, and speculation spread across the world. Was this it? Was the star entering its final stage? Was humanity about to watch a supernova unfold in real time? At the time, no one could say for sure. But now, with Webb's infrared precision, the mystery has only deepened and intensified. For the first time, we are supposedly seeing real-time indicators of a star in collapse. Massive energy discharges, shifting convection across its surface, and magnetic fields twisting into chaotic patterns. Betelgeuse is not simply dying in a poetic sense. It is transforming right in front of us. And Webb has been watching closely. For months, the James Webb Space Telescope has focused on Betelgeuse using instruments capable of seeing through layers that older observatories could never penetrate. Infrared observation reveals structure hidden beneath glare and dust, exposing the star's outer behavior in extraordinary detail. Now the data has arrived, and the picture it paints is staggering. Enormous convective bubbles, some described as the size of Jupiter, appear to burst across the star's surface. Plumes of hot gas stream into space at immense speed. Buried in the light spectrum is what is interpreted as a shock signature moving through the star's outer layers. If this interpretation holds, astronomers are not merely observing a bright star flicker. They are watching the physical anatomy of stellar destruction unfold as it happens. Not a simulation, not a model, not an artist's reconstruction, a real star in real time, beginning to come apart just 642 light-years from Earth. That distance is crucial, so far away that we see only the flare in its fading aftermath. Betelgeuse, by contrast, is close in cosmic terms, close enough that its eventual explosion could appear incredibly bright in our sky, possibly even visible in daylight, brighter than the full moon for a time. But brightness is only part of the story. Betelgeuse's proximity creates a once-in-a-generation scientific opportunity. It gives researchers a chance to study in detail how a massive star dies, how the core collapses, how outer layers are expelled, how shock fronts move, and how heavy elements are forged and scattered into surrounding space. That matters because supernovae are not just endings. They are factories of creation. Elements like carbon, oxygen, and many of the heavier ingredients necessary for planets and life are formed in stars and released in violent stellar deaths. What Webb is said to be capturing is not only the destruction of a star, but the process that seeds future worlds, the same cosmic cycle that ultimately made Earth and us. In that sense, this is framed as our ancestry in reverse, watching the source material of life being thrown back into the galaxy. The event, then, is more than spectacle. It becomes a key to hidden processes behind stellar evolution, galaxy formation, planetary systems, and the ongoing cycle of matter in the universe. Through Webb's advanced instruments, scientists can model the final stages of stellar death with far greater precision than before. They can test ideas that, for decades, were mostly theoretical. They can refine what signals to look for in other unstable stars, and perhaps one day predict future supernovae long before the final blast. That is why this is described not just as science, but as revelation, a moment when humanity looked into the abyss of time and saw the light explode back. And the consequences do not stop at the star itself. The explosion of Betelgeuse in this account is not a single flash and fade. It sends shockwaves outward across space, disturbing the interstellar medium around it. Webb has reportedly detected early ripples, high-energy particles moving away from the star, surrounding gas clouds heating up, and changes forming in the structure of Betelgeuse's dust halo. Then comes an even more dramatic possibility, a gravitational shift. The collapse of a stellar core can generate gravitational waves, ripples in space-time itself. If Betelgeuse's collapse produced them, and if those signals are confirmed and linked directly to the visible event, it would mark a historic milestone, the first time a visible nearby supernova has been paired with direct gravitational wave data in a clear, integrated way within this narrative. Such a connection would not just add another discovery to a list. It would reshape how we study the relationship between light, matter, and space-time, how one cosmic event can be measured across multiple forms of evidence at once. And as the collapse deepens, one of astronomy's oldest questions returns. What remains? When a giant star dies, the remnant can become a neutron star, a black hole, or something less familiar depending on mass, rotation, asymmetry, and how the collapse unfolds. The Webb data described here suggests Betelgeuse's collapse may not be perfectly uniform. There are hints of magnetic field disruption, plasma voids, and possible asymmetric fallback, material that fails to escape and is pulled back inward. That kind of uneven collapse raises the stakes. Some astrophysicists, the script notes, are speculating about a transitional object, something between a neutron star and black hole, theorized but never directly observed. If Webb has captured evidence of such a state in progress, it would amount to the first direct glimpse of a new class of cosmic object. Not just a spectacular death, but a category-defining discovery. Naturally, when people hear that a giant star only 642 light-years away is exploding, the next question is immediate. Are we in danger? The short answer, as presented here, is no. Betelgeuse is not close enough to threaten Earth directly. The longer answer is more nuanced. A supernova releases high-energy particles, gamma radiation, and expanding electromagnetic effects. While not catastrophic for us at this distance, such an event could influence local cosmic dust structures, alter conditions in surrounding space, and affect how light from other regions reaches Earth. In other words, even if humanity is physically safe, our view of the universe may change. That is why Webb's continued monitoring matters. Scientists are tracking the velocity and spread of the radiation front, watching how the star's death reshapes its environment. The event may become not only an astronomical spectacle, but a shift in the optical and physical context of our galactic neighborhood. And through all of it, Betelgeuse becomes something larger than an object of study. It becomes a reminder, massive, ancient, brilliant, and powerful, yet still mortal. Even stars, the lights we instinctively treat as permanent, have limits. What Webb has captured is framed not merely as a dying star, but as a cosmic mirror. Everything that exists has an ending. But in the universe, endings are rarely simple destruction. They are transformation. From Betelgeuse's death, new elements spread. From those elements, new stars may form. New planets may eventually emerge from the debris. New chemistry, new systems, new possibilities. In that sense, the explosion is not only collapse, it is renewal. And humanity for once was present to witness it. Now, among Webb's enormous stream of data, another unexpected detail reportedly emerged: variations in the elemental composition of the ejected material. Betelgeuse, according to this narrative, is releasing not only familiar stellar products like carbon, oxygen, and iron, but rarer elements such as technetium and yttrium, elements associated with extreme stellar environments. Why does that matter? Because the ratios of those elements act like a chemical fingerprint. By analyzing them, scientists can trace how matter moves through the galaxy, from the core of a dying star, into interstellar dust, into forming planets, and eventually into living systems. Webb is not just recording a dramatic event, It is decoding the chemistry of possibility. In that view, Betelgeuse's final act is also a message. A story written in elemental ratios, beginning long before Earth existed and continuing into whatever comes next. Betelgeuse itself will not return. Its familiar red point in Orion will eventually give way to an expanding cloud of superheated gas and glowing debris. The shoulder of the hunter will change. A pattern humans have recognized for thousands of years will be rewritten. But its death is framed here as a gift of knowledge, of material, of perspective. It reminds us that our own sun will not shine forever, that even the brightest lights have a final act, and that without supernovae, without these violent endings, there are no rocky planets, no oceans, no chemistry rich enough for life, no Earth, no us. Thanks to the James Webb Space Telescope, this narrative says, we are finally witnessing that full cycle with unprecedented clarity. Fiery collapse, elemental release, and the raw ingredients of creation sent back into the dark. In the cold silence of space, 642 light years from Earth, a star has ended its life. Not with a whisper, but with a brilliant final roar that traveled for centuries before reaching us. And because of Webb, we did not just see it. We understood it. We saw signs, collapse, and detonation, not as myth or metaphor, but as observable fact within this account. Betelgeuse did not die in vain. In its final moment, it offered answers to questions older than humanity itself. Where do the elements come from? How do stars live and die? What will one day happen to our own sun? In that fading red light, Webb captured more than a supernova. It captured an origin story and a glimpse of the future. So now the question changes, Dot. If the universe has revealed this, what else is it waiting to show us? And are we ready to witness what comes after the stars?